record. Okay, so I'm going over the review sheet, problem 1. We have the function of two variables, z is 1 minus x minus y. And the first part is to sketch the level curves for three different values of z. So if z is equal to 0, that means 1 minus x minus y is 0, which means x plus y equals 1. So this is the level curve in the xy plane. So this is the level curve, z equals 0. Right? If z is 0, 1 minus x minus y is 0, so x plus y equals 1. That's that line. For z equal 2, 1 minus x minus y, this is the same as x plus y equals minus 1. So that's this curve, this straight line. This is the level curve for z equal 2. This is minus 1 and minus 1. And for z equal to negative 2, if negative 2 was 1 minus x minus y, that means x plus y equals 3. So that's the level curve, the straight line that looks like that. That's the level curve, z equal to negative 2. So my three level curves, for this function, a level curve is a straight line, and that's what it looks like. Now, if we want to sketch the graph of the function, so we want to sketch the graph of the function, z equal 1 minus x minus y in three-dimensional space. That means this is all the points where x plus y plus z equals 1. So for example, the point 1, 0, 0 satisfies that. And the point 0, 1, 0 satisfies that. And the point 0, 0, 1 satisfies that. And in fact, if you take the triangle through those points, that's part of a plane. In fact, the graph of this function is a plane. It's a plane in three-dimensional space. And it's the plane that intersects the x, y, and z axes at the points, at these 3 points. In general, a plane in 3 space is of the form ax plus by plus cz equals d. So every plane satisfies an equation like this, and every equation of this form specifies a plane. So this is definitely a plane. And once you know it's a plane, if you can find 3 points on the plane that are not collinear, that determines the plane. So it's the plane in 3 space that goes through this triangle. Question about that? Okay. Problem 2 is a similar question for a different function. So for problem 2, we have a function z. It's some function of x and y, which is x squared plus y squared. So for the level curve z equal 1, it's all points where x squared plus y squared equals 1. That's just a circle of radius 1. So this is the level curve z equal 1. For the level curve z equal 4, x squared plus y squared equals 4. That's just a circle of radius 2. So the circle of radius 2 is the level curve z equal 4. And for z equal 9, you're looking at all points where x squared plus y squared equals 9. That's the equation of a circle of radius 3. So for this function, the level curves are all circles around the origin. That's what they look like. And if you want to graph this or sketch a graph in three-dimensional space, so we have z is x squared plus y squared. So for example, when x and y are at 0, the value of the function is 0. For any point on the line, in fact, if you let y equal 0, just if you, or sorry, let's say we let x equal 0. So in the YZ plane, those are the points where x is 0. This is just z equals y squared. It's just a parabola. And in fact, the graph of this is the paraboloid. It's like this rotated parabola. That's what it looks like. So this is the graph of the function. This is a paraboloid. And on the circle of radius r, you're at height r squared above that. So if you take the cross section for any value of z, it cuts this in a circle, and it's just the part of the curve above the level circle in the xy plane. But the graph of this function is a paraboloid. Okay. Questions about that?
Excuse me, Professor, are you gonna be uploading this lecture today or till the weekend?
No, I try to upload the lectures as soon as possible after it's over.
Yeah, because I don't think you uploaded last lecture yet. Lecture
Lecture
16.
16?
Yeah, because I'm on
Well, when I
the.
finish, I'll check, but I'm going to, if I haven't uploaded it, I definitely will.
All right, thank you, Professor.
Okay. Problem 3 is to find some limits. So if we want to take the limit as x, y, z approaches the point 1, 2, 3 of this polynomial, this is a continuous function. You just have to plug in the values for x, y, and z. 1, 2 squared times 3 minus 1 cubed 2, 3 squared. So that's 12 minus 18. So the limit is minus 4.
Professor, where do you get 12?
4 times 3. When x is 1, y is 2, and z is 3, this is 1 times 2 squared times 3, which is 1 times 4 times 3, or 12. Right? I'm just evaluating this limit.
Is it -6 the result?
Oh, sorry, thank you. 12 minus 18. Definitely -6. Thank you. All right. In the second limit, we have the function 4x squared minus 9y squared over 2 root x minus 3 root y. And I'm taking the limit as xy goes to the point 4, 4. So again, as xy approaches 4, 4, this denominator doesn't approach 0. So this is just 4 times 4 squared minus 9 times 4 squared over 2 times the square root of 4 minus 3 times the square root of 4. So this is 4 times 16 minus 9 times 16. over 4 minus 6. I have minus 2 there and 80. So it looks like this is just minus 40.
Professor,
Yeah,
you have 9 minus 6 in the square root.
sorry,
You have 9 minus 6, right? Sorry,
4.
You see, okay, 4.
Yeah, 2 times 2.
Right, thank you.
What's the result again? Minus 40, 80 over -2.
That's the result. But I think what I had really wanted to state as a problem is the limit as xy approaches the point 9 comma 4 of 4x squared minus 9y squared over 2 root x minus 3 root y. And in this case, when x is 9 and y is 4, this denominator is 0. So you can't just plug in. And the numerator also in this case is 0. You get 36 minus 36. But in fact, if you have 4x squared minus 9y squared, let's see, so what can we do? This is 2x minus 3y, 2x plus 3y. Yeah, I should have made this 4x minus 9y. That would have been a more interesting problem. So just, let me just solve this problem, even though it's not the one that's on the review sheet. We have the limit of 4x minus 9y over 2 root x minus 3 root y as xy approaches 9 comma 4. And in this case, if you were just to plug in these numbers, you would get 0 over 0. But in fact, 4x minus 9y actually does factor. This is 2 root x minus 3 root y times 2 root x plus 3 root y. And so if you take this and you divide by 2 root x minus 3 root y, these terms cancel, and you're left with 2 root x plus 3 root y. So this is the same as the limit as xy approaches 9, 4 of 2 root x plus 3 root y. And this does have a limit. It's 2 times square root of 3 plus 3 times the square root of 4. Sorry, 2 times the square root of 9 plus 3 times the square root of 4, which is 6 plus 6, or 12. So this function does have a limit, but it's not continuous at this point. In problem 3, we want to find the limit of x squared plus 2xy minus 6x plus y squared minus 6y over x plus y minus 6, and the limit as xy goes to 3, 3. So as x and y both approach 3, x plus y approaches 6, so the denominator goes to 0. The numerator goes to 9 plus 18, which is 27, minus 18, which is 9, plus 9, which is 18, minus 18. The numerator and the denominator both go to 0, so you can't just plug in. And the question is whether in some way this denominator, the numerator factors and you get the denominator out of it. So let's just experiment with this. This is just high school algebra technique. X squared plus 2xy minus 6x plus y squared minus 6y. So from this, let me factor out an x. I get x times x plus 2y minus 6. And from this, if I factor out a y, I get y times y minus 6. And I can write this as x times x plus y minus 6 plus another y plus xy plus y times y minus 6. So this is x times x plus y minus 6 plus y times x plus y minus 6. So in fact, this expression is equal to x plus y times x plus y minus 6. So if I take this and divide by x plus y minus 6, this fraction is exactly x plus y. So I really just need to compute the limit as xy, it goes to 3 comma 3 of x plus y, and that's 3 plus 3. So the limit is 6. Okay. So this is kind of a skill to be able to do this kind of factorization, but that's what you're expected to be able to do. Problems 4 and 5 are simply computing some partial derivatives. So in 4, we have a function of 2 variables, a polynomial, in fact. So if we want the partial of f with respect to x, derivative of x cubed is 3x squared. 3 times 7 is 21, x squared y. Derivative of x squared is 2x, so I get minus 2 times 2x minus 4x, y to the 5th. Derivative of x is 1. Derivative of y with respect to x is 0, and derivative of a constant is 0. So that's the partial of f with respect to x. Partial of f with respect to y is 7x cubed minus 10x squared y to the 4th plus 7x minus 9. If I differentiate this again with respect to x, I get 2x times 21, I get 42xy minus 4y to the 5th. If I differentiate this again with respect to y, this is 0. This is derivative of y to the 4th is 4y cubed. So I get minus 40x squared y cubed. And these don't involve y, their derivatives are 0. That's the second partial of f with respect to x. If I take the partial of f first with respect to x and then with respect to y, I'm differentiating this with respect to y, I get 21x squared minus 4x times 5y to the 4th minus 20xy to the 4th plus 7. And if I differentiate f first with respect to y and then with respect to x, I'm differentiating this with respect to x. I get 21x squared minus 20x y to the 4th plus 7. And of course, you'll notice these two are the same because for functions with continuous derivatives, the order of differentiation doesn't matter. If you differentiate first with respect to x and then with respect to y, or alternatively, first with respect to y and then with respect to x, you get the same answer. All right, any questions about this? If g of xy, this is problem 5, is e to the cosine of x times y, partial of g with respect to x, you differentiate this with respect to x, you get minus sine xy times the derivative of xy with respect to x, which is y, e to the cosine xy. And the partial of g with respect to y is, I have e to the cosine xy. If I differentiate this with respect to y, I get minus sine xy times x. And if I take, all right. Any questions about this? Right. The derivative of e to a function is the derivative of the function times e to that thing. So the derivative of cosine xy with respect to x is minus sine of xy times y. That's what you get.
Oh, Professor, if it was sine to the e, it would be cosine.
Yes,
For, okay. Thank you.
plus the cosine. And now if we look at the various second partial derivatives. So if I differentiate this again with respect to x, so I have the partial of g with respect to x is minus y sine of xy e to the cosine xy. So if I differentiate this again with respect to x, it's minus y, just by the product rule, partial of sine of xy with respect to y times e to the cosine xy minus y times the sine of xy times the partial with respect to, oops, this should be with respect to x, partial with respect to x of e to the cosine xy. Right? That's the product rule. So the derivative of the sine of xy with respect to x is the cosine of xy times y times minus y is minus y squared e to the cosine xy minus y sine of xy. When I differentiate this, I get another minus the sine of xy times y e to the cosine of xy. So minus times minus is plus, this is plus y squared sine squared of xy. So when I put all this together, I have an e to the cosine xy in both terms.
Professor, can you move your, oh, never mind.
And I also have a y squared in both terms. And here I have minus cosine of xy plus sine squared of xy. So if I'm lucky and I did this correctly, that's the answer. That's the second partial derivative of g with respect to x. And so on. I mean, I don't want to do all of these. It's just technical business of computing partial derivatives. And if I do them all, I'll run out of time and not get through the review sheet. Problem 6 and 7 are problems using the chain rule. So in problem 6, we have a function z of x and y. It's x cubed y squared minus 7xy to the fourth. But x is a function of t squared, a function of t, and y is a function of t. So z, well, all right. So z is really a function of t, and we want to be able to find dz dt. And to find dz dt, we need to know 4 other derivatives. The partial of z with respect to x is 3x squared y squared minus 7y to the fourth. The partial of z with respect to y is 2x cubed y minus 28xy cubed. The derivative of x with respect to t is 2t, and the derivative of y with respect to t is 3t squared. And what is dz dt? dz dt is the partial of z with respect to x dx dt plus the partial of z with respect to y dy dt. And I've just calculated these 4 derivatives. This is 3x squared y squared minus 7y to the fourth times 2t plus 7x cubed, sorry, plus 2, this is a 2, plus 2x cubed y minus 28xy cubed times 3t squared. And you can leave the answer like that, or you could plug in what x and y are equal to in terms of t, and you would get the answer as a function of t. But that is the chain rule applied to find dz dt. In problem 7, we have z is a function of x and y, but x and y are functions of 2 variables, s and t. X is s minus t squared, and y is s e to the t. And by the chain rule, the partial of z with respect to s is the partial of z with respect to x times the partial of x with respect to s, plus the partial of z with respect to y, partial of y with respect to s. So the partial of z with respect to x, if you differentiate sine xy with respect to x, you get y cosine of xy, and partial of x with respect to s is 1. Partial of z with respect to y is x cosine of xy. Partial of y with respect to s is e to the t. So that's the answer. And partial of z with respect to t is, again, by the chain rule, partial z with respect to x, partial x with respect to t, plus partial z with respect to y, partial y with respect to t. And you just plug in the appropriate things, and partial of x with respect to t is minus 2t. Partial of y with respect to t is se to the t. Okay. In question number 8, we have a function of 2 variables, x cubed y squared minus 7xy to the fourth again. What is the gradient? The gradient, by definition, is the partial of f with respect to x in the I direction plus the partial of f with respect to y in the j direction. If you take the partial of f with respect to x, you get 3x squared y squared minus 7y to the fourth I. Partial of f with respect to y is 2x cubed y minus 28 xy cubed j. That's the gradient. And the gradient at the point 2, 3, you just evaluate this when x is 2 and y is 3. When x is 2, this is 4. When y is 3, this is 9. So 4 times 9 is 36. Times 3, this is 108. Minus 7 times 81. Right, y to the fourth, 3 to the fourth is 81. 7 times 81 is 561. And when x is 2 and y is 3, this is 8, 16. 48 minus 28 times 3 cubed is 27 times 2 is 54. And then just calculate what these numbers are. Let me actually calculate this. 561, 108, if I subtract, this is minus 453i. Let's see, 28 times 54, 32. Two, 1, 5, 1. I subtract 48 from that. That's the gradient at the point 2, 3. And the directional derivative of f in the direction u. So u is a unit vector, 1 over root 2, 1 over root 2. It's the gradient of f at 2, 3, dot product with u. So that's equal to minus 453 over root 2 minus 1564 over root 2. So whatever that turns out to be is what it is. 4 and 3 is 7. 6 and 5 are 1. 2, 0. All right. This is the number. That is the directional derivative of this function in the direction of this unit vector. Okay. Questions about this? Any of this so far? Okay, this was problem 8, which means the next problem is problem 9. So here we have a function of 3 variables. I wrote g of xy, but it should have been g of xyz. X cubed y squared z minus 7 xy to the fourth plus x z cubed. So the gradient of g, you take the partial with respect to x, 3x squared y squared z minus 7y to the fourth plus z cubed I. Partial of g with respect to y, 2x cubed yz minus 28xy cubed plus 3 xz squared j. And the partial with respect to z is x cubed y squared plus 3xz squared k. And if I want to calculate the gradient at the point 1, 2, 3, I just have to do this calculation. So when x is 1, y is 2 is 4 times 3 is 12. This is 36 minus 7 times y to the fourth. Y to the fourth is 81. 81 is 567 plus z cubed, y to the fourth. Y is 2. So y to the fourth is 16. And 16 times 7 is 112. And z cubed is 27. And the j component at 1, 2, 3 is 2 times 2 is 4 times 3 is 12 minus 28 times 1 times 8. 28 times 8 is possibly 224. Plus
Professor,
3.
Professor,
Yeah,
you said 28 y to the third.
I'm sorry. What are you asking?
Yeah, that one is 28x minus s y to third, right?
So 28xy cubed. So x is 1 and y is 2. So this is 8.
Okay.
28 times 8 is, I think, 224.
Okay.
And 3xz cubed, x is 1, z is 3. So this is 3 times 9, or 27. And for this is 1 times 4 plus 3 times 9. So let's see, whatever this is I don't know, 36 plus 27 is 63 minus 112, 112. So if you subtract, I think you get 49. And 12 and 27 is 39. And 224 minus 39 is maybe 185. Plus 81. So I would have to check this, but this, 4 plus 27 is 31. So the gradient of G is something like this. And if we want the directional derivative of G in the direction U, where U is 1 over root 2, 1 over root 3, 1 over root 6. So if I take the length of U squared, that's a half plus a third plus a sixth, which is 1. So this is a unit vector. So this is the gradient of G dot product with U. So I get some, messy expression minus 49 over root 2 minus 185 over root 3 plus 31 over root 6. Whatever number this is the directional derivative of the function G in the direction of U.
Professor.
Right.
Professor,
Yes,
I have a question.
go ahead.
How did you get to on the second line for vector I and J? Where do you get that?
Which is the second line? This line
Yeah, where do you get vector I and the last one J?
and then K,
No, J, this, right, the second line.
right? So you want to know where this came from?
Yeah, and high, the first one high.
Oh, okay, so this is G. So the partial of G with respect to X is 3x squared y squared z. I'm differentiating with respect to X. Everything else is a constant.
Yes.
Minus 7y to the fourth plus x cubed. Sorry, plus z cubed. So that's exactly what I have here.
So you call it I, right? You call it vector I?
Well, I don't, no, I don't call it the vector I. The vector I
Where do you get I?
is the vector 1, 0, 0. J is the vector 0, 1, 0.
Okay,
K is the vector 0, 0, 1. These are the standard unit vectors in three-dimensional space. This is just a number. This is the component of this vector in the X direction. So if you have a vector ABC in three-dimensional space, that's
Sure.
the same as A times I plus B times J plus C times K.
Okay.
Right? These are just alternate ways of writing vectors.
I got it now. Thank you.
Okay. Let me just do one more thing. So the next couple of problems, we need the tangent planes. So let me just pause for a minute. So the general expression for a tangent plane, there's several equivalent ones, but actually there are really two that we look at. So if you have the surface f of x, y, z equals 0, the tangent plane at the point ABC is given by the partial of f with respect to x at ABC times x minus a plus the partial of f with respect to y at ABC times y minus b plus the partial of f with respect to z at ABC, z minus c equals 0. And if your function is given in the form z equals some f of x, y, and so then the tangent plane at the point AB and f of AB is given by z is the partial of f with respect to x at AB times x minus a plus the partial of f with respect to y at AB times y minus b plus the value of the function at ab. So this is the form that is most reminiscent of the tangent line and the linear approximation to a function of one variable from first year calculus. So for problem number 10, we want to find the equation of the plane tangent to the surface x squared plus y cubed plus z to the fourth equals 2, first at the point 1, 0, 1. So this is like you're looking at a function f of x, y, z equals x squared plus y cubed plus z to the fourth minus 2 equals 0. That's just to get it to look in this form. And we have to know the partial derivatives at this point. So partial of f with respect to x is 2x. So the partial of f with respect to x at 1, 0, 1 is 2. Partial of f with respect to y is 3y squared. So the partial of f with respect to y at 1, 0, 1 is 0. When y is 0, this is 0. Partial of f with respect to z is 4z cubed. So the partial of f with respect to z at 1, 0, 1 is 4. So my tangent plane looks like 2 times x minus 1 plus 0 times y minus 0 plus 4 times z minus 1 equals 0. This is 2x minus 2 plus 4z minus 4 equals 0. 2x plus 4z equals 6, or x plus 2z equals 3. So this is the equation of the tangent plane at the point 1, 0, 1. And at the point 1, 0, minus 1, you get slightly different numbers in a slightly different tangent plane. Okay. In problem 11, we have z as a function of x and y, and we want to find the tangent plane at 2 points on the surface that this defines. So here, in problem number 11, z is 4 minus 2x squared minus y squared. And if you look at the point 2, 2 minus 8, when x is 2 and y is 2, you get 4 minus 8, which is minus 4. Minus 4, you get minus 8. So this point lies on this surface. And the tangent plane so partial of f with respect to x is minus 4x. And when x is equal to 2, this is minus 8. So we get the tangent plane z equals minus 8 x minus 2. Partial of f with respect to y is minus 2y. When you evaluate this, when y equals 2, you get minus 4. So minus 4, y minus 2. And when x is 2 and y is 2, we already saw this is minus 8. So z is equal to minus 8x plus 16 minus 4y plus 8 minus 8. So this is minus 8x minus 4y plus 16. So we have the tangent plane 8x, well, z equals this, if you like. Or you could rewrite it as 8x plus 4y plus z equals 16. So these are equivalent. Okay. And problem 12 is another problem to calculate the tangent plane. Here z is x squared e to the x minus y. And when x and y are both equal to 2, z is equal to 4. So this is 1 point on the surface. When x and y are both equal to -1, you get 1 times e to the 0. So -1 minus 1, 1 is another point on the surface. Let's calculate a tangent plane. We need the partial of z with respect to x is 2x e to the x minus y plus x squared e to the x minus y. And if we evaluate this at the point 2, 2, this is 2 minus 2 is 0, e to the 0 is 1. You get 4 plus 4 is 8. And the partial of z with respect to y is x squared e to the x minus y times -1. And again, if you evaluate this at 2, 2, you get -4. So my tangent plane at the point 2, 2, 4 is 8 times x minus 2, z equals 8 times x minus 2 minus 4 times y minus 2 plus 4, or 8x minus 16 minus 4y plus 8 plus 4, 8x minus 4y minus 4. So that's the tangent plane. Now, the important application of tangent planes is as a linear approximation. So 13 and 14 are just calculating linear approximations. In problem 13, we have f of xy is xy plus x minus y. Partial of f with respect to x is y plus 1. Partial of f with respect to x at the point 2, 3 is 4. Partial of f with respect to y is x minus 1. Partial of f with respect to y at the point 2, 3 is 2 minus 1 or 1. So my tangent plane is z equals 4 times x minus 2 plus 1 times x minus times y minus 3, which is 4x plus y minus 8 minus 3 minus 11. oops, sorry. What is f of 2, 3? It's 2 times 3 plus 2 minus 3 is 6. 8 minus 3 is 5 plus 5. So this is 4. So z is 4x plus y minus 8 minus 3 minus 11 plus 5 minus 6. Yeah. So that's the tangent plane. And we want to use this to estimate f at 2.1, 2.99. So the value of the function at this point is approximately 4 times 2.1 plus 2.99 minus 6. This is 8.2 plus 2.99 minus 6. So if I add this up correctly, this is 8 and 2 are 10, 11.19 minus 6 is 5.19. So at this point, 2.1, 2.99, the value of the function is approximately 5.19.
Professor,
Yeah,
how do you get 8.2?
sorry.
How do you get 8.2?
So this is my tangent plane, 4x plus y minus 6.
Yes.
So when x is 2.1 and y is 2.99, this number is 4 times 2.1, which is 8.2, plus y plus 2.99. This is 4x plus y.
Okay. Thank you.
Let's see. If I get a calculator and actually calculate this exactly, let me see what I get. So f of 2.1, 2.99 is exactly equal to xy plus x minus y. So this is equal to 2.1 times 2.99 plus 2.1 minus 2.99. I get 5.39. So this is an approximation, and this is the exact value.
Professor,
Yeah,
this one is not clear to me though.
I'm sorry, it's what?
This one is not clear to me. Where you have 4.2.1, it's supposed to be 8.4, right? But you say 0.2.
Oh, no, I just did the arithmetic wrong. Thank you.
Okay.
8.4, yes.
Oh, all right, I got it now.
Actually, good. That gives me a better approximation too. So
Mm.
this is actually, it's almost exact, at least the 2 decimal places. This gives me 5.39. And the true value to 2 decimal digits is also 5.39.
Okay. Thank you.
Professor, now that you're done doing the review, are you gonna do any more like review problems or anything like that for the rest of class?
I'm sorry, say that again, please.
What's it's because we just finished the review. Can you do a couple like more like I guess like problems like kind of like the ones that are on the review, but like change like the numbers or like anything like that, or is
Yeah,
Is
sure.
this the-
So what type of problem would you like me to?
Yeah, Professor, can you do number 5 again?
or like a problem like what's it can you do what's it he wants to do that I would want to do another gradient function problem if you can.
Right. And what was the other question about? I just didn't hear what you said.
Number 5.
Number 5?
Yeah.
Let's see if I can find number 5. Oh, number 5 is just calculating partial derivatives. Sure, I can do more of those. Oh, what I didn't do is the very last problem. So let me do that one also, just for completeness. I just did number 13. Let me do number 14. So for a function of 3 variables, this is problem 14. F of x, y, z is the log of 1 plus x plus y plus 2z. And at the point 0, 0, 0, this function has the value 0. So the tangent plane or the linear approximation, let's call it W, is so what is the partial of f? Let me just calculate these derivatives. The partial of f with respect to x is 1 over 1 plus x plus y plus 2z. Partial of f with respect to y is 1 over x plus y plus 2z. Partial of f with respect to z is 1 over x plus y plus 2z times 2. And when I evaluate this at 0, 0, 0, this is 1, this is 1, and this is 2. So my linear approximation to this function is W equals partial of f with respect to x at x minus 0, plus the partial of f with respect to y, y minus 0, plus partial of f with respect to z, z minus 0, plus the value of the function is 0, 0, 0. So this partial derivative is 1, and so this is just x. This is 1 times y. This is 2 times z, and f of 0, 0, 0 is 0. So this is my linear approximation. And at 0.1 minus 0.2 plus 0.2, the value of this function is approximately 0.1 minus 0.2 plus 2 times 0.2. So this is 0.5 minus 0.2 is 0.3. So that's what my linear approximation would be. Okay. Now, in terms of partial derivatives, it's just a lot of, solving the problems. If you had z is equal to x to the 5th, y to the 4th, partial of z with respect to x is that. Partial of z with respect to y is that. Second partial of z with respect to x is that. Second partial of z with respect to y is that. If I take the partial of z first with respect to x and then with respect to y, when I differentiate this with respect to y, I get 4 times 5 is 20. I get that. If I take the second partial of z first with respect to y and then with respect to x, I differentiate this with respect to x, I get 20 x to the 4th y cubed. And of course, these are equal. For this function, if I want the gradient, it's 5x to the 4th y to the 4th I plus 4x to the 5th y cubed j. That's the gradient. That's all it is. All right. I'm going to have several problem sessions over the next few days and also on the weekends. So there'll be plenty of time to log in and ask questions that you might have.
Will you post it in an announcement, for the class, Professor?
Yeah,
Your,
of course. I mean,
okay.
otherwise, there's no way to tell.
All right, thank you, Professor. And you said you're gonna upload this, this lecture today so we can study it?
As soon as we're done.
All right, thank you, Professor, for
Okay.
everything.
All right, so that's it for today. And again, I'll send out an email with times for problem sessions over the next couple of days in the week. Okay, bye all.